everybody. This is Dr. Dadu presenting Pure Maths 3 HSC Maths. Happy listening. Now, it's the third in the series. If you've been following it, you'll have seen 1 and 2. This time around, I intend to talk about integration by parts. There's a technique that is inside integration of parts known as reduction formula and its application. Just like the so-called mighty formula is based upon methods of completing the squares, the reduction formula is also based upon integration by parts. All right. So this is how it works. We are going to look at an integrand. Most of the time, it is a rather complicated integrand that we'll be looking at. We will now use method of integration by parts on it. And as we do so, we will generate an expression that can be used to further resolve the complicated integrand. Look at what is happening here. Look at this integrand, for instance. By the time you start doing integration by parts on it, you arrive at this equation 1 that reduces the complexity of it. And it's in terms of I, the integral. Okay, so equation 1 can be used to generate some other results. Now, if we have something like this to bargain with, you see, it's a special type of this for m equals 3. And by the time you do integration by parts, you have this. And you utilize the result, equation 1. Utilize equation 1. Then you have this with ease. You can now further look at this. It will be a mere replication. Just be repeating the exploit of equation 1. You will be having results. And at the end of the day, you generate the solution to this integral. Now, you have one here to look at your leisure anyway. Now, most times, the complicated integrand is usually a trig ratio of, for instance, sine raised to power m theta. By the time you start integration by parts, you reduce it to this. And this is interesting because at some instances, this part of it vanishes, leaving you with this. And this is very, very useful, as we'll see later. Okay, now let's assume we have this result, equation 1. Okay, at this instance at which m is equal to 0, you know this will be integration of the theta, and that will be theta. So for m equals 2, 4, 6, 2n, even powers, what will result is different from the situation in which n is odd. When n is even, the result, okay, this is an instance where n is 2, even. The result is different from when n is odd, which is an example of what I have here. And again, there's something that is worthy of note, the interval. If it is to evaluate the integrand in an interval, then some other things will also come in. Okay, so let's see further examples. For that series, if m is 0 and is supposed to be evaluated in this interval, this is what results. If m is equal to 2, this is what results. M equals 4. So for even m, this is what will be resulting. You don't have to carry out any integration. Just look at the power. Is it even or odd? If it is even, This is what gives you the result. Now, if it is odd, there will be no pi in the scene. No pi in the scene. This is what will give you the result. Examples are the ones I've shown here. All right. These are very easy examples that follows from that. Further applications now. If you are in the interval 0 theta, the example we've been looking at is in the interval 0 pi over 2. If you are in 0 pi, then you are going to study the integrand and see how it behaves in the first quadrant, in the second quadrant. Sometimes it will be positive in the first quadrant. They're all positive in the first quadrant now. I mean, trig ratios are positive in the third quadrant. Tan, sine, cos are all positive in the first quadrant. But it depends on the integrand you have in your hands. So when you know where it is positive and where it's negative, you know what to cancel out. Here, for the sine function, because sine is more or less usurping the minus sign, just like an even function, it will split, because we can easily find that the integration from pi over 2 to pi will be the same thing as from 0 to pi over 2. And that will just give us 2 of that, which is what I have in here. Integration from 0 to pi is just giving us 2 of this. See, giving us 2 of from 0 to pi over 2. And since we all can easily evaluate this, that is equal to this. Now, if it is for cos, for instance, the cos function does not usurp the minus in the argument. As such, it will not be equal to 2 of it. It will have minus 1 raised to power m in front of this one. So such that from the integral from 0 to pi of it will be this. To be this. And again, that will enable you to find other results. Yeah, there is something that is also worthy of note. Because if you don't know how it behaves in the quadrants, you may not know. And if you don't know the nature of m as to whether it is even or odd, you may not know when this minus 1 will be usurped. You may not know. If m is even, for instance, you know minus 1 raised to power m will vanish. It will be 1. And so that this will now be twice. But when n is odd, you don't bother integrating it, to be 0. Just in this case, it will be 0. It just cancels out. When n is even, it will be this. It continues like that. That is the farthest I intend to go. I have a short time to discuss this, but that's why I've been very detailed with the note. Take time to read the notes if you don't grab it at the first instance. Please like, share, and subscribe. Thanks for listening. Bye for now. Thank you. See you next time when I come up with another one. Thank you.